Across the observable universe, there are structures so large that light itself needs hundreds of millions of years just to cross them. For decades, cosmologists believed the early universe was too young, too chaotic, and too small to build anything truly massive. Galaxies were supposed to emerge slowly. Structure was supposed to take time. Then James Webb looked deeper than any telescope in human history ever had. In 2022, Webb began detecting galaxies so old, so massive, and so chemically evolved that several astronomers immediately realized something was wrong. These were not primitive fragments forming in the aftermath of the Big Bang. They looked mature, structured, ancient. One of them, now called Jade's GSZ 140, existed just 290 million years after the beginning of the universe, and it already contained hundreds of millions of stars. According to the standard model of cosmology, that should not have been possible. There simply was not supposed to be enough time for matter to collapse, ignite into stars, explode into supernovae, seed heavy elements, and then repeat the process enough times to build a galaxy like that. But Webb did not stop at one impossible galaxy, it found dozens. Then astronomers noticed something even larger, a colossal structure stretching across roughly 1.3 billion light years of space. A near perfect ring of galaxies arranged on scales the universe was never supposed to organize itself into. A structure so large that it appears to violate one of the foundational assumptions behind modern cosmology itself, the idea that, at large enough scales, the universe should look statistically uniform in every direction. At the same time, another problem has continued growing quietly in the background. Two completely different methods of measuring the expansion rate of the universe keep producing two completely different answers. The gap between them has survived every attempt to remove it. Three anomalies, three different scales, and all of them may be pointing toward the same possibility that our current model of the universe is incomplete. Quick favor before we continue. If you find yourself coming back to videos like these, hit subscribe so you don't miss the next one. It makes a bigger difference than you might think. The story begins with the model cosmologists believed explained how the universe built itself. For most of cosmic history, the universe was expected to behave like a patient machine. Not dramatic, not sudden, just slow accumulation across unimaginable spans of time. The modern model describing that process is called lambda cold dark matter, usually shortened to lambda CDM. It is the framework behind nearly every major prediction in cosmology for the last several decades. And until Webb began sending data home, it worked remarkably well. In the beginning, matter was almost perfectly smooth. Not completely smooth, though. Tiny irregularities existed inside the young universe, fluctuations smaller than the thickness of a fingerprint across cosmic scales. These uneven regions came from quantum fluctuations, microscopic variations in energy created during the universe's earliest moments. Inflation, the violent expansion immediately after the Big Bang, stretched those fluctuations across space itself. Gravity took over from there. Over hundreds of millions of years, slightly denser regions attracted more matter. More matter increased gravity. Stronger gravity pulled in even more material. Slowly, the universe began organizing itself. First came diffuse clouds of hydrogen and helium. Then the first stars ignited. Galaxies emerged afterward, followed by clusters of galaxies, and eventually the vast cosmic web stretching across billions of light years. But the important word is slowly. Gravity is powerful, but it is not fast. Matter cannot collapse instantly. Gas heats up, radiation pushes outward, supernova explosions disrupt formation, Every stage introduces resistance. According to Lambda CDM, building a large mature galaxy requires billions of years of layered growth and repeated mergers between smaller systems. Dark matter accelerated this process. We cannot see dark matter directly because it does not emit or absorb light, but we detect its gravity everywhere. Galaxies rotate too quickly without it. Clusters hold together because of it. In the Standard Model, dark matter formed enormous invisible halos first, long before stars appeared. Ordinary matter then fell into those halos like rainwater settling into valleys. Without dark matter, galaxies would form far too late for the universe we observe today. To measure this timeline, astronomers use redshift. Redshift is the stretching of light caused by cosmic expansion. As the universe expands, light traveling through it becomes stretched into longer wavelengths, shifting toward the red part of the spectrum. The farther away an object is, the more stretched its light becomes. That makes redshift a kind of cosmic clock. Higher redshift means we are looking deeper into the past. Hubble could glimpse some of those distant epochs, but only faintly. Its instruments struggled to resolve the earliest galaxies clearly enough to measure their structure and chemistry. Webb was designed specifically for this frontier. Its infrared instruments detect ancient stretched light invisible to Hubble, allowing us to observe galaxies from only a few 100 million years after the Big Bang. And according to every major simulation, galaxies at redshift 10, 12, or 14 should be small, chaotic, fragmented objects, proto-galaxies, barely assembled, brief sparks inside a still forming universe. That was the expectation. Then Webb opened its mirror. On July 12th, 2022, the first Webb Deep Field image appeared on screens around the world. At first glance, it looked familiar. A dark background crowded with scattered points of light, warped arcs, and distant galaxies layered across space. Astronomers had seen deep fields before. Hubble spent decades staring into tiny black regions of sky and revealing thousands of hidden galaxies. Webb's image seemed like the next step in that tradition, but the details arrived quickly. Within days, research teams began isolating faint objects from the image and measuring their redshifts. Software pipelines processed infrared signatures late into the night. Candidate galaxies started appearing at redshifts above 10, then above 12, then higher still. Objects from a universe only a few 100 million years old were suddenly everywhere in the data. The problem was not merely distance, it was brightness. Astronomers use something called the Schechter limit to describe the expected upper brightness range of galaxies in a young universe. The idea is statistical. In earlier cosmic epochs, galaxies should remain relatively small because there has not been enough time for gravity to gather large amounts of matter into stable structures. Extremely luminous galaxies should therefore become exponentially rarer the farther back we look. But Webb kept finding them. One team, led by astronomer Ivo Lebey, identified six unusually massive galaxy candidates hidden inside Webb's earliest observations. Their estimated stellar masses were staggering. According to prior Lambda CDM simulations, the combined amount of starlight implied by those six galaxies rivaled the total expected stellar mass for the entire observable universe at that epoch. Not one region, the entire universe. Inside private discussions between researchers, disbelief spread almost immediately. Some assumed calibration errors, others suspected contamination from closer objects mimicking distant signatures. One astronomer reportedly summarized the mood with a single sentence: "We just broke the universe." But nobody rushed to announce that publicly. The data moved through months of rechecking. Photometric analysis, meaning estimates based on brightness and color alone, was not enough. Extraordinary claims required spectroscopy, the technique that splits incoming light into precise wavelengths and reveals exact chemical and distance information. Spectroscopy removes ambiguity. It locks galaxies into place along the cosmic timeline with far greater certainty. Teams requested additional observing time. Independent groups repeated the measurements using separate methods. Peer reviewers pushed back hard. Mass estimates were revised downward in some cases, but even conservative revisions left the galaxies far larger and brighter than expected. The tension remained. Then the spectroscopic confirmations arrived. Several of the candidate galaxies were exactly where Webb first indicated they were, deep inside the infant universe. Their light had traveled more than 13 billion years before reaching Webb's mirrors. Some already showed signs of mature stellar populations, organized structure, and chemical enrichment that should have required far longer to develop. The strange part was no longer hypothetical, it was measured. And these were still only isolated galaxies, individual points scattered through the dark. Once astronomers widened the frame and examined how matter itself was arranged across enormous distances, the scale of the anomaly became harder to contain. Long before the public heard the name Jade's GSZ 140, Webb had already been staring into the same narrow regions of sky for months at a time, not scanning broadly, watching deeply. The program responsible was called the James Webb Advanced Deep Extragalactic Survey, shortened to JADES. It became the most ambitious deep field campaign ever attempted, combining the power of Webb's infrared instruments with hundreds of accumulated observation hours focused on ancient galaxies near the edge of visibility. The strategy was simple in principle: look longer, see earlier. As exposure time increased, dim objects hidden behind cosmic expansion slowly emerged from the darkness. Thousands of galaxies appeared inside regions once thought nearly empty. Some were faint smudges, others resolved into compact structures with surprising brightness and shape. Every additional hour pushed the observable universe further backward in time. Then came May of 2024. That was when astronomers spectroscopically confirmed Jade's GSZ 140, the most distant galaxy ever verified. Its measured redshift was 14.32. In plain language, we are seeing this galaxy exactly as it existed only 290 million years after the Big Bang, not 1 billion years after, not even 500 million, 290 million. By itself, distance was not the real shock. Webb was built to reach extraordinary distances. The deeper problem was what existed there once the light arrived. Jade's GSZ 140 already contained hundreds of millions of solar masses worth of stars. Solar mass simply means the mass equivalent of our sun, used by astronomers to compare cosmic objects on a manageable scale. The galaxy was bright, chemically active, and unexpectedly mature. According to standard structure formation models, galaxies at that epoch should still be fragmented collections of unstable star forming regions. They should not yet possess substantial stellar populations, organized structure, or advanced chemical signatures. But Webb spectroscopy revealed something else inside the galaxy's light: oxygen. That single element changed the interpretation completely. The early universe began mostly with hydrogen and helium. Heavier elements, what astronomers call metals, are forged inside stars through nuclear fusion. Oxygen forms only after stars live, burn through their fuel, and eventually die, often in violent supernova explosions that scatter those elements into surrounding gas clouds. New stars then form from that enriched material. That cycle takes time, more than the timeline comfortably allows. For oxygen to exist inside Jade's GSZ 140, Earlier generations of stars had already formed, evolved, exploded, and seeded new stellar nurseries before the galaxy emitted the light Webb detected. Multiple generations of stellar evolution had somehow unfolded within less than 300 million years of cosmic history. The implications settled heavily across the field. The universe was building complexity almost immediately. Some researchers proposed unusually efficient star formation. Others explored altered feedback mechanisms, exotic dark matter behavior, or underestimated gas densities in primordial halos. But no explanation removed the pressure entirely. Jade's GSZ 14.0 remained difficult to reconcile with the expected pace of cosmic evolution. And it did not arrive alone. Across the Jade survey, more galaxies appeared, carrying the same quiet contradiction, each one suggesting that the young universe had become structured, luminous, and chemically mature far earlier than our models ever anticipated. A single impossible object can sometimes be ignored. Astronomy has a long history of apparent anomalies fading under better measurements or improved calibration. One strange galaxy does not immediately threaten an entire cosmological framework. Statistical outliers happen naturally inside large data sets. Scientists expect them, but Webb did not find one. It found populations. Astronomers describe those populations using galaxy number counts, a statistical prediction for how many galaxies of a certain mass should exist at a particular redshift. The calculation comes directly from lambda CDM simulations. If the early universe evolved gradually, then massive galaxies should remain extremely rare at high redshift because there simply has not been enough time for matter to assemble into large stable systems. The prediction curves were very clear. Webb crossed them repeatedly. At redshifts above 10, observed galaxy counts began exceeding theoretical expectations by factors of 10, sometimes 100, depending on the mass range and model assumptions used. In practical terms, Webb was finding entire categories of galaxies far more often than the standard model allowed. Not slightly more often, orders of magnitude more often. That difference matters enormously. Cosmology depends on probabilities. A theory can survive occasional tension, but persistent statistical failure forces something deeper into question. In 2023, astrophysicist Philip Boylan Colchin published one of the first major papers attempting to formally quantify the scale of the discrepancy. The paper carried a restrained title, Stress Testing Lambda CDM with High Redshift Galaxy Candidates. The conclusions were less restrained. Under standard cosmological assumptions, some of Webb's early galaxy detections possessed probabilities lower than 1 in a million. That does not mean impossible in an absolute sense. The universe is vast enough that extraordinarily unlikely events can still occur. But when multiple low probability detections appear together across independent observations, the statistical pressure compounds rapidly, and the galaxies themselves kept becoming stranger. One of the clearest examples was GNZ 11, originally detected before Webb, but observed afterward in far greater detail. Webb's spectroscopy revealed unusually strong nitrogen emission lines inside the galaxy's light spectrum. Nitrogen abundance matters because it traces earlier generations of stellar activity and chemical enrichment. Standard stellar evolution models struggle to produce that amount of nitrogen so early without requiring accelerated cycles of star birth and death operating under unfamiliar conditions. The pattern widened carefully, almost quietly. The galaxies were too luminous, too massive, too chemically evolved. Their shapes appeared more organized than expected. Some showed compact disk structures, others contained mature stellar populations where only primitive star forming regions should have existed. Each observation alone invited debate. Together, they formed a consistent direction of tension. The early universe looked busy, far too busy. Researchers proposed revised star formation efficiencies, modified feedback behavior, hidden active galactic nuclei, or underestimated dust corrections. Some solutions reduced parts of the discrepancy, none erased it entirely. The same underlying problem remained visible beneath every adjustment. Cosmic structures seemed to emerge earlier and faster than the timeline comfortably permitted, and these tensions were still confined to individual galaxies, isolated systems separated by immense darkness. Once astronomers began examining structure across hundreds of millions and then billions of light years, the scale of the mismatch expanded beyond single objects altogether. If you could drift far enough above the observable universe, beyond individual galaxies and clusters, the cosmos would not look random at all. It would resemble an enormous interconnected network, long luminous strands crossing darkness, dense intersections glowing with thousands of galaxies, vast empty regions between them, almost completely abandoned by matter. Astronomers call this arrangement the cosmic web. Its architecture emerges from gravity, acting across immense spans of time. Dark matter halos form first, creating invisible gravitational wells throughout space. Ordinary gas falls inward afterward, cooling and condensing into stars and galaxies. Those galaxies gather along elongated filaments shaped by dark matter itself, while emptier regions lose material and become voids. Over billions of years, the universe separates into walls, nodes, filaments, and hollow expanses stretching across hundreds of millions of light years. The scale is difficult to picture. Entire galaxy clusters become small features inside larger structures. The Milky Way is not even a grain in this framework. It is part of the local group, which belongs to the Virgo supercluster, itself embedded inside the larger Laniakea structure, and even Laniakea dissolves into broader patterns once surveys expand far enough outward. But according to standard cosmology, there should be a limit. This idea is called the cosmological principle. In plain language, it means that although small regions of the universe can vary dramatically, the universe becomes statistically uniform at sufficiently large scales. Above roughly 300 million light years, matter should average out smoothly. No direction should appear fundamentally special. No individual structure should dominate the overall distribution. That assumption carries enormous weight. General relativity, when applied to the universe as a whole, depends on large-scale uniformity. Calculations involving cosmic expansion rely on it. Interpretations of the cosmic microwave background rely on it. The entire lambda CDM framework quietly assumes the universe behaves this way once you zoom out far enough. For years, observations mostly supported the picture. Then astronomers began finding structures that pressed uncomfortably against the boundary. One example was the Sloan Great Wall, discovered in 2003 through the Sloan Digital Sky Survey. It stretched roughly 1.37 billion light-years across, a massive concentration of galaxies extending far beyond earlier expectations. Later came the Hercules Corona Borealis Great Wall, estimated at nearly 10 billion light-years in length, based on gamma-ray burst distributions. That second structure created immediate debate. Some researchers questioned whether it represented a genuine connected system or a statistical artifact caused by incomplete sampling. Others argued that observational biases exaggerated its apparent size. The structure remained controversial enough that cosmology absorbed the tension without fully breaking under it. That pattern repeated often. Large anomalies appeared. Researchers debated uncertainties. Statistical explanations softened the implications. The cosmological principle survived because each individual challenge could still be framed as an edge case, an improbable fluctuation inside an otherwise functional model. But the atmosphere surrounding those discoveries gradually changed. The universe was beginning to look less uniform than expected, especially once deeper surveys mapped matter distributions with greater precision. Patterns emerged across distances once assumed safely smooth, and in 2024, astronomers identified a structure whose geometry, scale, and coherence became far more difficult to dismiss as coincidence or measurement error alone. The discovery did not begin with a telescope image dramatic enough for headlines. It began with pattern analysis, statistical mapping, and the slow sorting of galaxy positions across enormous catalogs of survey data. Hidden inside those coordinates, Alexia Lopez, then a doctoral student at the University of Central Lancashire, noticed something unusual while studying information from the DESI Legacy Imaging Survey. The arrangement curved, not loosely, precisely. The structure became known as the Big Ring, a colossal circular distribution of galaxies and galaxy clusters spanning roughly 1.3 billion light-years in diameter. Its measured redshift was approximately zero point 0.8, meaning we observe it as it existed around 6.9 billion years ago, when the universe was roughly half its current age. Its apparent size in the sky was astonishing. If you could somehow see the entire structure with your eyes alone, it would stretch across a region 15 times wider than the full moon. Yet despite that enormous scale, the galaxies followed a remarkably coherent geometry. The distribution did not resemble the elongated filaments normally produced by gravitational clustering. It was not a random overdensity or a diffuse wall. The galaxies traced something disturbingly close to a ring. That shape matters deeply. The universe produces strands, knots, clusters, and sheets through gravitational evolution. Simulations reproduce those forms naturally because matter collapses unevenly along dark matter scaffolding over billions of years. But a near-circular arrangement this large does not emerge cleanly from known cosmological mechanisms. The geometry itself became part of the anomaly, and the timing intensified the discomfort. In January of 2024, Lopez presented the Big Ring at a meeting of the American Astronomical Society. Many astronomers attending already recognized her name because 1 year earlier, at another conference, she had introduced a different large-scale anomaly called the Giant Arc. The Giant Arc was even larger, stretching approximately 3.3 billion light-years across. It appeared as a massive crescent-shaped arrangement of galaxies occupying the same general region of sky as the Big Ring. It existed at nearly the same redshift as well, suggesting both structures belonged to a similar cosmic epoch. That coincidence proved difficult to ignore. Independent anomalies can sometimes survive statistical scrutiny, but two giant coherent structures appearing close together inside the same cosmological neighborhood drastically lowers the probability of random chance explanations. The issue was no longer only size. It became clustering, geometry, and alignment all at once. Lopez addressed the tension directly in public statements. Neither of these structures is predicted by current cosmological theory. The sentence spread quickly through astronomy circles because it was unusually blunt. Most researchers describe anomalies cautiously, emphasizing uncertainty and incomplete data. But the underlying issue was hard to soften. Existing simulations did not naturally produce structures like these, especially not together. Some astronomers proposed observational bias, Others suggested that human pattern recognition might exaggerate coherence inside sparse galaxy distributions. Additional mapping and statistical analysis became essential. But even critics acknowledged the same underlying fact. The structures existed in the data and demanded explanation. And once the Big Ring entered cosmology discussions, the possible explanations narrowed toward three uncomfortable directions, each carrying consequences far larger than the structure itself. By the time the Big Ring entered mainstream discussion, cosmologists had already narrowed the possible explanations into a small and uneasy set. None were fully satisfying. Each solved part of the puzzle while creating new problems somewhere else. And beneath all three possibilities sat the same uncomfortable reality. The universe was no longer behaving as cleanly as our models preferred. The first explanation was the least disruptive. Maybe the structure was simply a statistical fluke. The observable universe contains hundreds of billions of galaxies spread across incomprehensible distances. In a cosmos that large, random clustering can occasionally mimic meaningful patterns. Human perception is also extremely good at imposing order onto incomplete information. A ring might not truly be a ring at all. It could be unrelated galaxy clusters accidentally aligned from our perspective. That argument carried weight initially, but probability becomes more fragile as anomalies accumulate. One rare structure can survive inside a statistical model comfortably. Two similar anomalies in neighboring regions become harder to dismiss. Additional oversized walls, arcs, and clustering irregularities compound the issue further. Independent flukes multiply probabilities against themselves. Eventually, the explanation begins relying on coincidence more heavily than the anomaly itself. The second hypothesis involved something real and already well understood. Baryon acoustic oscillations, usually shortened to BAOs. In the early universe, before atoms fully formed, matter existed as a hot plasma where radiation and particles moved together in enormous pressure waves. Those waves rippled outward through space, much like sound traveling through air. When the universe cooled enough for atoms to stabilize, the ripples froze into the large-scale distribution of matter itself, leaving behind faint preferred distances between galaxies. Astronomers still detect those imprints today. BAOs are one of cosmology's strongest observational successes. They help measure cosmic expansion and support the standard model remarkably well. The problem is scale. Typical BAO structures appear around 490 million light-years across. The Big Ring spans roughly 1.3 billion light-years, nearly 3 times larger. Its geometry also fails to match expectations. BAOs produce broad statistical shells and clustering signatures, not coherent near circular arrangements with consistent structure across enormous distances. Which leaves the third possibility. The cosmological principle itself may be incomplete. If the universe is not statistically uniform at the largest scales, then some regions may genuinely contain more structure, denser clustering, or different expansion behavior than others. That idea reaches far beyond galaxy surveys. Nearly every major cosmological calculation assumes large-scale uniformity somewhere in its foundation. Remove that assumption, and many derived measurements become uncertain simultaneously, including the expansion rate of the universe. This connects directly to another growing tension inside cosmology, the Hubble tension. Measurements based on the early universe, especially from the cosmic microwave background, produce one value for cosmic expansion. Measurements taken from nearby galaxies and supernovae produce another. The disagreement sits around 8 to 9%, and instead of shrinking as instruments improve, The discrepancy has become sharper. Some researchers now wonder whether these problems are related. If matter distribution across the universe is genuinely uneven at immense scales, local measurements of expansion could differ naturally from global measurements without requiring entirely new physics. Inhomogeneity alone might distort our cosmic perspective enough to create the mismatch. But even if the cosmological principle survives intact, Webb uncovered another tension, untouched by geometry or large scale structure altogether, a problem measured not across space, but across time itself. At the center of all these discoveries sits a problem so simple it almost feels unreasonable. Galaxies require time to build, not metaphorical time, physical time. Gas must collapse, stars must ignite. Heavy elements must form inside stellar cores. Supernovae must scatter those elements outward. Gravity must gather matter repeatedly across expanding space. The universe is estimated to be 13.8 billion years old. Some of Webb's galaxies appear mature after only a fraction of that history. Astronomers describe this using look-back time, a direct measure of how far into the past we are observing when light reaches our telescopes. At extreme redshifts, Webb is not offering simulations or reconstructions. It is recording ancient photons that physically traveled across cosmic expansion for more than 13 billion years before arriving at its detectors. This is observation, not prediction. When Webb observes a galaxy at redshift 14, we are seeing an object from roughly 290 million years after the Big Bang. The issue is not whether the galaxy exists. The issue is how it became so large, so quickly, under known physical constraints. To build a galaxy containing 10 billion solar masses worth of stars in that time frame requires astonishing efficiency. Star formation efficiency refers to the percentage of available gas inside a galaxy that successfully becomes stars. In nearby galaxies, observed efficiencies typically range between 10 and 30%. Much of the gas never reaches stellar ignition because radiation pressure, stellar winds, and supernova explosions expel material back into interstellar space. Galaxies regulate themselves naturally. They waste enormous amounts of matter. But Webb's early galaxies seem to violate that behavior. Some implied mass estimates require star formation efficiencies approaching 50, 70, or even 100%, depending on the assumptions used. At those levels, nearly all available gas would need to collapse into stars with almost no interruption from feedback processes. Standard models struggle badly there. Stars are violent objects. Massive stars explode quickly and inject enormous energy into surrounding gas clouds, slowing additional collapse. That feedback mechanism is one of the core stabilizing assumptions built into cosmological simulations. Remove or weaken it significantly, and galaxy growth accelerates dramatically. So researchers face several possibilities. Perhaps star formation operated differently in the infant universe, under conditions no longer present today. Perhaps primordial gas clouds were denser, colder, or more gravitationally unstable than current models assume. Perhaps hidden matter reservoirs existed that our measurements underestimate. Or perhaps something even more foundational is incomplete. The age itself. In 2023, Rajendra Gupta proposed a controversial interpretation suggesting the universe may be closer to 26.7 billion years old. His model combined evolving physical constants with alternative cosmological assumptions designed to reduce the timing tension created by Webb observations. Most cosmologists remain unconvinced. The proposal conflicts with several well-established measurements, especially those involving the cosmic microwave background and large-scale expansion history. But the response to Gupta's paper revealed something important. Researchers debated the mechanisms heavily, yet many acknowledged the underlying pressure driving the discussion. Webb had exposed a legitimate timing problem that demanded explanation somewhere inside the model, because age alone cannot fully resolve the tension. Even if the universe were older, the question of matter itself would remain. These early galaxies still require enormous amounts of mass assembled at extraordinary speed, concentrated into structures that seem to arrive too early and too complete. Cosmology keeps a running inventory of everything believed to exist in the universe. According to the current standard model, only about 5% consists of ordinary matter, the atoms forming stars, planets, gas clouds, oceans, and living things. Around 27% is dark matter, invisible material detected through gravity alone. The remaining 68% is dark energy, the unknown component associated with cosmic expansion accelerating over time. Almost everything is hidden, and in the early universe, even the visible fraction began nearly smooth. Tiny density variations existed after the Big Bang, but they were extraordinarily subtle. The cosmic microwave background shows fluctuations measured in fractions of a percent. Matter was not born inside giant clumps ready to become galaxies. It had to gather gradually through gravitational attraction across expanding space. That is where the numbers become difficult. To produce the massive galaxies Webb observes at extreme redshift, those tiny overdensities needed to collapse much faster than standard gravitational evolution comfortably allows. Gas had to accumulate rapidly inside dark matter halos, cool efficiently, resist feedback disruption, and sustain intense star formation almost immediately after the first structures appeared. Gravity alone struggles to keep pace. Some researchers therefore began revisiting an older and highly unusual possibility: primordial black holes. Unlike ordinary black holes formed from collapsing stars, primordial black holes would have emerged directly from density fluctuations in the universe's first seconds, long before stars or galaxies existed at all. That distinction changes everything. If primordial black holes formed early enough, they could have acted as gravitational anchors scattered throughout the infant cosmos. Gas would fall inward around them naturally, accelerating structure formation dramatically. Instead of galaxies beginning from diffuse clouds alone, some may have grown around pre-existing compact objects already massive enough to organize surrounding matter quickly. Webb has intensified interest in this idea because it keeps finding black holes that appear impossibly mature for their age. At high redshifts, astronomers now observe active galactic nuclei, intensely luminous regions powered by supermassive black holes, consuming matter at their centers. Several of these black holes already possess millions of solar masses, less than 1 billion years after the Big Bang. Under standard growth models, this becomes extremely difficult to explain. One example sits at redshift 10.1. The black hole's estimated mass approaches 10 million suns. Under ordinary accretion physics, meaning growth through gradually consuming nearby gas, a stellar mass black hole born from a dying star should not have enough time to reach that scale. Even sustained feeding near theoretical maximum rates struggles to produce such rapid expansion. The clock runs out first. Primordial black holes offer one way around the problem because they bypass the stellar stage entirely. Instead of beginning as small remnants from exploded stars, they may have emerged already massive during the universe's earliest moments. Some cosmologists even propose that dark matter itself could partially consist of primordial black holes distributed throughout space. But evidence remains incomplete. No confirmed primordial black hole has ever been directly identified. The hypothesis solves certain timing tensions while introducing new uncertainties involving inflation, gravitational lensing, and early universe stability. Yet the idea continues gaining attention because Webb keeps exposing systems that appear older, heavier, and more developed than expected. Whether the answer involves primordial black holes, modified gravity, hidden matter reservoirs, or some entirely unknown process, the pattern has become increasingly difficult to dismiss. Somewhere inside our model of cosmic structure formation, an important ingredient appears to be missing. Long before galaxies existed, before stars ignited or planets formed, the universe released a faint field of radiation that still surrounds us now. Every direction in space contains it, not visible to human eyes, but measurable with extraordinary precision. Astronomers call it the cosmic microwave background, or CMB, the oldest light in the universe. It emerged roughly 380,000 years after the Big Bang. Before that moment, the universe was too hot and dense for light to travel freely. Electrons and protons moved through space as an opaque plasma, scattering radiation constantly. But as expansion cooled the cosmos, those particles combined into neutral hydrogen atoms, light finally escaped and began crossing the universe uninterrupted. We still detect it today. The CMB matters because it preserves a direct snapshot of the infant universe before stars, galaxies, or large structures complicated the picture. Tiny temperature variations embedded inside that radiation reveal where matter was slightly denser or slightly thinner in the beginning. Those minute fluctuations became the seeds from which every future galaxy and cluster eventually formed. Modern cosmology rests heavily on this map. The most detailed version came from the Planck satellite, launched by the European Space Agency in 2009. Planck measured temperature differences across the sky with astonishing sensitivity, detecting variations smaller than 100,000th of a degree. From those measurements, cosmologists extracted precise values for the universe's age, composition, expansion rate, and matter distribution. The data fit lambda CDM remarkably well. Using the CMB as a starting point, simulations could evolve the universe forward mathematically, predicting how structures should grow over billions of years. The resulting models produced expected distributions for galaxy masses, clustering scales, dark matter halos, and star formation histories at different epochs. Those predictions are exactly what Webb is now challenging. Because the early structures Webb observes appear too large, too bright, and too mature compared to what the CMB-based models forecast, the disagreement does not emerge from vague interpretation. It emerges from comparing direct observation against statistical expectations rooted in the most precise cosmological dataset humanity has ever collected. And the CMB itself contains strange details. One example is the cold spot, an unusually cool region spanning nearly 1 billion light-years in apparent size. Some researchers believe it may correspond to a supervoid, a genuinely underdense region of space containing far less matter than expected. If true, it introduces tension with the assumption of perfect large-scale uniformity. Another anomaly is the hemispherical asymmetry. One half of the sky displays slightly stronger temperature fluctuations than the other. Multiple analyses across different instruments have confirmed the pattern persists beyond ordinary noise, yet no standard explanation fully accounts for it. The imbalance is subtle, but persistent enough to remain scientifically uncomfortable. None of these anomalies alone overturn cosmology, but together they create a growing unease. The CMB remains our cleanest window into the early universe and our strongest foundation for predicting cosmic evolution. Yet the structures that emerged afterward, especially those Webb now observes directly, do not align neatly with what those predictions anticipated. We are left in a peculiar position. Two of humanity's most powerful instruments are describing the same universe in different ways. One maps the universe near its beginning with exquisite precision. The other photographs what eventually formed from those beginnings. Somewhere between those two pictures, something important still escapes our understanding. For decades, dark matter has functioned as the hidden framework beneath modern cosmology. Galaxies rotate too quickly without it. Galaxy clusters remain gravitationally bound because of it. Large-scale structure simulations only reproduce the observed universe once enormous amounts of invisible mass are included. Without dark matter, galaxies form far too slowly, and the cosmic web never fully develops. In the standard picture, dark matter comes first. Soon after the Big Bang, invisible dark matter began collapsing into dense halos spread across the universe. Ordinary matter, mostly hydrogen gas, then drifted into those gravitational wells. The gas cooled, fragmented, and ignited into stars. Galaxies emerged afterward, nested inside halos already assembled by unseen mass. That sequence solved many earlier problems. But Webb introduced a new one. Even with dark matter included, some of the halos required to host Webb's earliest galaxies should not exist at redshift 14. The predicted timeline still struggles. Matter has not had enough time to gather into structures massive enough to support the galaxies now being observed. Dark matter accelerates formation dramatically compared to ordinary matter alone, yet Webb's galaxies continue arriving ahead of schedule. This has reopened older debates. One alternative receiving renewed attention is modified Newtonian dynamics, usually called MOND. Proposed by physicist Mordechai Milgram in the 1980s, MOND does not add invisible matter to the universe. Instead, it modifies how gravity behaves at extremely low accelerations. Under certain conditions, gravity becomes effectively stronger than standard Newtonian predictions would allow. That adjustment changes structure formation. Some MOND-based cosmological models produce faster early galaxy growth than conventional dark matter simulations. In those formulations, matter can collapse more rapidly during the universe's first epochs, potentially easing some of the tension created by Webb's observations. A few researchers now argue that the unexpectedly mature galaxies at high redshift resemble MOND predictions more closely than standard lambda CDM forecasts. But MOND carries serious problems of its own. While it explains some galactic rotation curves elegantly, it struggles badly at larger scales. Galaxy cluster dynamics remain difficult to reproduce under MOND alone. The detailed temperature fluctuations inside the cosmic microwave background also align far more naturally with dark matter-based cosmology. In those areas, lambda CDM still performs much better. The debate, therefore, shifted toward another possibility. Perhaps dark matter exists, but behaves differently than assumed. Standard cosmology usually relies on cold dark matter, meaning hypothetical particles moving relatively slowly in the early universe. Cold dark matter naturally forms small structures first, which later merge into larger galaxies and clusters. But some physicists now explore warm dark matter models instead, where particles move faster and suppress certain small-scale structures while altering large-scale collapse timelines. Different particle behavior changes cosmic architecture subtly. The challenge is that no dark matter particle has ever been directly detected despite decades of experiments underground, in particle accelerators, and through astrophysical searches. Evidence for dark matter's gravitational effects remains overwhelming, but its physical nature is still unknown. That uncertainty matters more now than it once did, because Webb is no longer testing only one part of cosmology at a time. Dark matter, dark energy, the cosmic microwave background, structure formation, galaxy evolution, all of them are being pushed simultaneously against observations arriving from the edge of the observable universe. In 1998, astronomers studying distant exploding stars discovered something the universe was never supposed to do. Expansion was not slowing under gravity as expected, it was accelerating. Galaxies were drifting apart faster over time, as though some unseen influence was steadily pushing space itself outward. That influence became known as dark energy. Today, dark energy is estimated to comprise roughly 68% of the universe's total energy content. Yet, despite dominating the cosmos numerically, its physical nature remains almost completely unknown. We cannot isolate it in laboratories. We cannot observe it directly. We infer its existence only through the behavior of expanding space across enormous distances. The leading explanation traces back to Albert Einstein. While developing general relativity, Einstein introduced a mathematical term called the cosmological constant, a repulsive energy embedded into space itself. He later abandoned the idea after evidence suggested the universe was expanding naturally. For decades, he reportedly referred to the constant as his greatest blunder. But after the supernova discoveries of the late 1990s, cosmologists restored the concept because it fit the acceleration data remarkably well. Under the standard model, dark energy remains constant forever. As space expands, dark energy continues driving galaxies farther apart, eventually producing a colder, emptier universe where distant structures disappear beyond the observable horizon. The mathematics are elegant, stable, predictable, but recent observations complicated the picture again. In 2024, the Dark Energy Spectroscopic Instrument, usually called DESI, released new data examining millions of galaxies and quasars across cosmic history. The results hinted, cautiously but persistently, that dark energy may not be perfectly constant after all. Its influence may have changed over time. That possibility alters everything downstream. If dark energy evolved differently in the past, then the expansion history of the universe changes with it. The timing of galaxy formation shifts. Estimates for cosmic age shift. Matter would have clustered under different conditions than current simulations assume. Structures, forming unusually early, might no longer appear quite so impossible if expansion behaved differently during the universe's first epochs. Some cosmologists, therefore, began exploring an extension of the standard model called W0WA CDM. The model modifies lambda CDM by allowing dark energy's strength to evolve gradually across time rather than remaining fixed forever. In several analyses, DESI's measurements fit this evolving dark energy framework slightly better than the traditional cosmological constant. Not dramatically better, but enough to attract attention. None of this proves dark energy changes. The statistical significance remains below the threshold physicists require for a formal discovery. Future data may erase the signal entirely. Yet, the broader atmosphere surrounding cosmology has shifted because Webb's findings already expose stress inside the standard timeline for structure formation. Now another pillar appears less stable too. And the strange part is how these tensions converge. The Hubble tension points toward problems in cosmic expansion history, Oversized structures challenge large-scale uniformity. Webb's galaxies compress the timeline of early formation. Deci hints that dark energy itself may evolve over time. None of these anomalies alone necessarily overturn modern cosmology. Together, they trace back toward the same ancient era, the first billion years. That convergence matters because it suggests our uncertainty may not lie inside isolated details, but inside the deeper conditions governing how the early universe itself behaved. Every new instrument sharpens the model while simultaneously exposing its edges. Webb did not uncover a single contradiction hidden in the dark. It illuminated an interconnected network of them. Across the observable universe, galaxies do not drift through space randomly. They gather along enormous strands shaped by gravity over cosmic time, forming a vast interconnected network that stretches farther than any individual cluster or supercluster. These strands are called filaments, dense rivers of dark matter and gas, extending hundreds of millions of light years between giant nodes packed with galaxies. Between them lie the voids, regions so empty that a spacecraft could travel for millions of years without passing near a major galaxy. The contrast is extreme. Matter collects into walls and threads, while immense volumes of space remain comparatively barren. Together, the pattern forms what astronomers call the cosmic web, the largest known structure in existence. The idea emerged theoretically during the 1980s. Computer simulations showed that gravity acting on dark matter naturally produces filamentary structure over billions of years. Matter does not collapse evenly. It flows inward along preferred pathways, accumulating where filaments intersect. Later surveys confirmed the prediction observationally. Projects like the Sloan Digital Sky Survey mapped millions of galaxies and revealed the web directly, a universe organized less like scattered islands and more like branching veins. But those surveys mostly examined the mature universe. Webb changed the timeline. For the first time, astronomers could study the cosmic web during its earliest stages, at redshifts where large-scale structure should still be primitive and loosely assembled. Instead, Webb began finding evidence that the web had already developed substantial organization far earlier than expected. One striking example appeared at redshift 6.7. That means the observed structure existed only around 800 million years after the Big Bang. Yet, Webb identified a protofilament spanning tens of millions of light years and containing multiple galaxy groups already clustered along a coherent structure. A protofilament is essentially a young version of the cosmic web, matter flowing into elongated regions before fully mature galaxy clusters emerge. The problem is timing again. Structures that large should require far longer periods of gravitational growth according to standard simulations. But Webb keeps observing matter already concentrated into organized overdensities deep inside the early universe. Some of the strangest objects associated with these regions are Lyman alpha blobs, enormous glowing clouds of hydrogen gas radiating intensely in ultraviolet wavelengths. Several extend across distances larger than modern galaxy clusters. Their energy sources remain debated. Some may be powered by active black holes, others by violent star formation or cooling gas collapsing into massive structures. Whatever drives them, they appear connected to regions of rapid assembly. Webb has also identified galaxy overdensities at high redshift, regions where galaxy counts exceed surrounding space by factors of 10 to 50. These concentrations resemble embryonic galaxy clusters, forming astonishingly early. Instead of isolated galaxies scattered evenly through the young cosmos, matter appears to collect into preferred environments almost immediately. That implication reaches backward through the entire timeline. If the cosmic web already possessed substantial structure by redshift 6 and 7, then the process organizing matter must have begun even earlier, possibly during epochs where radiation, dark matter behavior, and primordial gas dynamics become extremely difficult to model accurately. Watching the cosmic web emerge is essentially watching the universe become recognizable to itself. The filaments, clusters, and voids visible around us today all grew from those first imbalances. But Webb's observations suggest the process did not unfold slowly and uniformly everywhere at once. Some regions seem to have accelerated ahead almost immediately, assembling structure while the rest of the cosmos was still barely beginning. Most of the universe is empty. Not empty in the casual sense, but profoundly empty. Regions where galaxies become sparse enough that millions of light years can pass between major structures. These regions are called cosmic voids, vast cavities suspended between the denser filaments and walls of the cosmic web. Together, they occupy most of the universe's total volume. They are part of the same process. As gravity pulls matter inward toward overdense regions, emptier regions lose material and become increasingly barren over time. Filaments grow denser, while voids grow larger. The cosmic web evolves from both directions at once, accumulation in some places, evacuation in others. Standard cosmology predicts this naturally. Dense structures and empty structures are two outcomes of the same gravitational flow, but some voids became difficult to classify comfortably. One of the earliest examples was the Boötes void, discovered in 1981 by astronomer Robert Kirshner and collaborators. Stretching roughly 330 million light years across, it contained dramatically fewer galaxies than statistical expectations suggested. Entire regions appeared almost abandoned by matter. At first, the discovery felt shocking. Then cosmology adapted. The Boötes void was eventually interpreted as a rare but acceptable fluctuation inside the broader distribution of large-scale structure. Unusual, yes. Impossible, no. The standard model survived because extreme emptiness can still emerge naturally in sufficiently large cosmic volumes. But another proposed void carried more unsettling implications. The KBC void, named after researchers Keenan, Barger, and Cowie, describes a possible underdensity centered near our own galaxy, extending roughly 2 billion light-years across. If accurate, it would place the Milky Way inside one of the largest known voids in the observable universe. That matters because our measurements depend on location. Astronomers determine cosmic expansion partly by observing how quickly nearby galaxies recede from us. But if we happen to live inside a large, underdense region, local space would expand slightly faster than denser regions elsewhere. That could systematically bias nearby measurements upward compared to measurements based on the early universe. Suddenly, the Hubble tension acquires geography. Instead of requiring entirely new physics, part of the discrepancy might emerge because our local cosmic neighborhood is not representative of the universe overall. The expansion rate we observe nearby would differ naturally from the global average inferred from the cosmic microwave background. The evidence remains debated. Some galaxy surveys support the existence of a local underdensity. Others find weaker signals or inconsistent boundaries. But Webb complicated the discussion further by mapping galaxy distributions at high redshift with much greater precision than earlier instruments allowed. The pattern appears exaggerated on both sides. Overdense regions in the early universe contain more galaxies than expected, while underdense regions appear emptier and more structured than simulations predict. The universe seems to have separated into extremes unusually quickly. Matter concentrated faster in some locations, while draining more efficiently from others. In other words, the young universe looked lumpier than it should have, not only through oversized galaxies or impossible large scale rings, but through the very texture of matter distribution itself. Density fluctuations appear amplified across multiple scales simultaneously. Too much structure here, too little there, faster growth everywhere. And because these anomalies emerge across such different environments, from isolated galaxies to billion light year voids, they begin raising a deeper question about where the imbalance truly begins. Before carbon existed, before oxygen drifted through galaxies, before iron formed inside collapsing stellar cores, the universe contained almost nothing except hydrogen and helium. The first stars emerged inside that chemically simple cosmos, forming from pristine gas untouched by any earlier generation of stellar death. Astronomers call them population 3 stars. None have ever been observed directly. They remain theoretical, reconstructed from simulations and the chemical fingerprints left behind in later cosmic structures. But according to modern cosmology, these stars changed the universe permanently. Their nuclear fusion forged the first heavy elements: carbon, nitrogen, oxygen, silicon, iron, the ingredients required for rocky planets, complex chemistry, atmospheres, oceans, and eventually biology itself. Everything heavier than helium began there. Population. 3 stars were expected to differ radically from stars we see today. Without heavy elements to cool collapsing gas clouds efficiently, simulations predict that early stellar nurseries produced extraordinarily massive stars, perhaps hundreds or even thousands of times more massive than the Sunday. Massive stars burn hotter and faster. Many may have survived only a few million years before exploding violently as supernovae or collapsing into black holes. Brief lives, enormous consequences. Standard models place their formation at redshifts above 20. Deep inside epochs Webb cannot yet observe directly. The halos hosting them should have been small, unstable, and scattered sparsely through the young universe. Those first stars would ignite, die quickly, and seed surrounding gas with the first metals long before mature galaxies emerged. But Webb may already be seeing their aftermath. Not the stars themselves, but indirect signatures encoded inside the spectra of ancient galaxies. Spectra are essentially chemical barcodes produced when matter absorbs and emits specific wavelengths of light. By studying unusual abundance ratios, astronomers can infer what kinds of stars existed earlier inside a galaxy's history. Several Webb observations show strange patterns. One recurring example involves GNZ11, the same galaxy whose rapid maturity already challenged standard formation timelines. Webb detected unexpectedly strong nitrogen signatures inside its spectrum, difficult to reproduce using ordinary stellar populations alone. A 2023 paper published in Nature proposed that compact clusters of population 3 stars may explain the anomaly. If correct, the implication is severe. For population, 3 stars to enrich galaxies observed at redshift 14, those stars must have formed, evolved, exploded, and recycled matter into new stellar generations at even earlier epochs, likely redshifts above 20. That pushes the timeline for cosmic structure formation into territory where current physics becomes increasingly uncertain. the universe would have ignited almost immediately, and Webb still cannot see that far directly. Cosmic expansion stretches light from those first stars so severely that many may remain permanently beyond observational reach. Some cosmologists suspect the true beginning of stellar history may never be photographed in a conventional sense because the earliest objects were too faint, too distant, and too rapidly evolving. Yet traces remain. Every oxygen atom inside an early galaxy, every anomalous nitrogen ratio, every chemically mature system appearing too soon carries information inherited from stars that no longer exist. The first stellar generation may be gone completely, but the material they forged continued traveling forward through cosmic history, embedded into later galaxies, and eventually into us. Webb is reading those traces carefully now, one spectrum at a time. At the center of nearly every large galaxy sits a black hole. Our own galaxy contains one called Sagittarius A, holding roughly 4 million times the Sun's mass inside a region smaller than our solar system. For most of modern astronomy, supermassive black holes were understood as ancient objects that grew slowly across billions of years. The standard pathway seemed straightforward. A massive star collapses at the end of its life, forming a stellar mass black hole, perhaps 10 or 50 times heavier than the Sunday. Over immense stretches of time, that black hole accretes gas, absorbs nearby matter, merges with others, and gradually increases in mass until eventually becoming supermassive. But growth has limits. As matter spirals inward, friction heats the surrounding disk intensely, producing enormous radiation pressure, pushing outward against infalling gas. The balance between gravity pulling inward and radiation pushing outward defines the Eddington limit, the theoretical maximum stable growth rate for a black hole. Even under ideal conditions, the process is slow. A stellar mass black hole growing continuously near the Eddington limit still requires billions of years to reach billions of solar masses. That timeline worked comfortably for galaxies in the nearby universe. Then Webb and earlier high redshift surveys started finding quasars. Quasars are among the brightest objects in existence. They are active galactic nuclei powered by supermassive black holes, consuming matter so rapidly that the surrounding disks outshine entire galaxies. Webb detected quasars at redshifts above 7, meaning they already existed less than 800 million years after the Big Bang. One example became especially difficult to explain. The quasar J0313-1806, discovered at redshift 7.64, hosts a black hole estimated at 1.6 billion solar masses. The light reaching us left that object when the universe was only around 670 million years old. The arithmetic does not cooperate. There simply is not enough time under standard growth models to build something that massive, starting from ordinary stellar remnants. Even aggressive accretion struggles to close the gap before the available cosmic clock runs out. So cosmologists began considering more radical possibilities. One proposal involves direct collapse black holes. Instead of forming from dying stars, these hypothetical objects would emerge when enormous primordial gas clouds collapsed directly into black holes during the early universe, bypassing normal stellar evolution entirely. Such seeds could begin already containing tens of thousands or even millions of solar masses. That shortens the timeline dramatically. Another possibility is super Eddington accretion, where black holes somehow consume matter faster than the theoretical growth limit ordinarily permits. Certain early universe environments may have trapped radiation differently, allowing unusually rapid feeding episodes before outward pressure halted infall. Both ideas remain speculative. No direct collapse black hole has been confirmed observationally. Sustained super Eddington growth has not been demonstrated at the scales required either. Yet the observations forcing these discussions continue accumulating because the black holes themselves are undeniably present in Webb's data, and they keep arriving too early. The black holes are too massive. The galaxies surrounding them are too evolved. The structures embedding those galaxies are too extensive. Across nearly every observable scale, the early universe appears more developed, more organized, and more accelerated than standard cosmology comfortably predicts. There was a period when the universe contained matter, but almost no visible structure. No galaxies illuminated the dark. No stars burned across intergalactic space. Hydrogen and helium drifted silently through expanding emptiness after the first transparent era faded into darkness again. Astronomers call this interval the cosmic dark ages. To understand it, we have to move back before the first stars existed. Immediately after the Big Bang, the universe was an intensely hot plasma where electrons and protons moved freely, scattering radiation constantly. Light could not travel uninterrupted because every photon collided repeatedly with charged particles. Then, the universe cooled. Roughly 380,000 years after the Big Bang, electrons combined with protons to form neutral hydrogen atoms. Radiation finally escaped freely through space, producing the cosmic microwave background and making the universe transparent for the first time. But transparency did not mean illumination. For hundreds of millions of years afterward, space remained dark because no stars yet existed to generate visible light. The universe contained gas, gravity, and expanding structure, but no luminous objects had fully ignited. Then something changed. The first stars and galaxies began flooding surrounding space with intense ultraviolet radiation. That radiation transformed the cosmos again. Ultraviolet photons carry enough energy to strip electrons away from hydrogen atoms, ionizing the gas between galaxies. This process is called reionization because it returned much of the universe to an ionized state after neutral hydrogen had dominated during the Dark Ages. The change reshaped everything. As more stars formed, bubbles of ionized gas expanded outward through intergalactic space until eventually they overlapped, making most of the observable universe transparent to ultraviolet light again. Cosmologists estimate this epoch of reionization largely completed around 1 billion years after the Big Bang near redshift 6. Earlier models imagined the transition unfolding gradually and relatively evenly, but Webb is revealing a more chaotic picture. Instead of smooth universal illumination, reionization now appears patchy and uneven, driven by concentrated regions packed with early galaxies, while neighboring regions remained neutral far longer. Some areas became intensely active very quickly. Others lagged behind. The universe seems to have brightened in islands rather than uniformly across space. That detail connects directly to Webb's larger anomalies. The same galaxy overdensities appearing unexpectedly early may also be the engines responsible for ending the cosmic dark ages. In other words, the galaxies considered theoretically inconvenient may have performed one of the most important transformations in cosmic history. Their ultraviolet radiation changed the physical state of the entire intergalactic medium. Webb identifies many of these distant galaxies using something called the Lyman break technique. Neutral hydrogen absorbs ultraviolet light very efficiently below specific wavelengths, As cosmic expansion stretches ancient light toward infrared wavelengths, astronomers can detect sharp spectral drop offs indicating extremely high redshifts. The method is remarkably reliable at great distances. Before spectroscopic confirmation even occurs, researchers can already estimate whether a candidate galaxy belongs to the earliest cosmic epochs simply by analyzing where that spectral break appears. Which means Webb is not merely glimpsing isolated ancient objects, it is tracing the moment when darkness itself began disappearing from the universe. The transformation from opaque silence into luminous structure was driven by objects that standard cosmology struggles to explain comfortably. Whatever those early galaxies truly were, they illuminated the cosmos around them. Galaxies are not supposed to grow without limits. Every major model of cosmic evolution includes mechanisms that slow star formation before a galaxy consumes all available gas. Astronomers call this feedback, the process through which stars and black holes regulate the environments that created them. Young stars are disruptive objects. Massive stars release ultraviolet radiation, stellar winds, and eventually supernova explosions powerful enough to heat and expel surrounding gas. That gas is the raw material required for future star formation. As more stars ignite, they gradually poison their own supply chain, reducing the efficiency with which galaxies convert gas into new stars. In modern galaxies, feedback is essential. Without it, simulations produce systems far too massive and luminous compared to observations. Feedback prevents runaway collapse. It slows growth naturally. Star formation efficiency remains relatively modest because galaxies constantly lose part of their available material back into surrounding space. But Webb introduced another contradiction. If feedback operated in early galaxies as effectively as it does today, many of the systems Webb observes should not have accumulated their enormous stellar masses quickly enough. The radiation from young stars and supernovae should have interrupted star formation long before those galaxies reached the sizes now being measured. Something behaved differently. Perhaps early galaxies were denser and more compact, allowing gravity to retain gas despite intense stellar activity. Perhaps lower metallicity, meaning fewer heavy elements inside primordial gas clouds, changed how efficiently energy transferred through those environments. Or perhaps feedback itself operated under physical conditions no longer common in the nearby universe. Then there is black hole feedback. When supermassive black holes actively accrete matter, the surrounding regions can release astonishing amounts of energy through jets, radiation, and high velocity outflows. This process is called AGN feedback, short for active galactic nucleus feedback. In some galaxies, it becomes powerful enough to heat or expel gas across enormous distances, effectively shutting down future star formation entirely. Galaxies can extinguish themselves. Webb has now identified surprisingly mature quenched galaxies at redshifts 4 and 5, systems that already stopped forming stars only 1 or 2 billion years after the Big Bang. A quenched galaxy is essentially one where star formation has largely ceased because the available cold gas has been exhausted, expelled, or heated beyond collapse. The timeline becomes difficult again. To produce a massive, quenched galaxy so early, star formation must have proceeded at extraordinary speed before abruptly shutting down. Entire galactic life cycles appear compressed into periods far shorter than standard cosmology comfortably predicts. Some of these objects are called red and dead galaxies. They contain older stellar populations emitting redder light while showing little evidence of ongoing star formation. Under earlier models, Galaxies at those redshifts should still appear actively assembling themselves, rich in gas and violently producing new stars. Instead, Webb finds systems that already resemble cosmic retirement homes, fully formed, quiet, ancient looking. The implication reaches beyond individual galaxies. Not only did the early universe build structure faster than expected, it also terminated that growth faster than expected. Formation and shutdown both appear accelerated simultaneously. Galaxies emerged rapidly, evolved rapidly, and in some cases went dormant rapidly. The ordinary pacing of cosmic history seems compressed almost everywhere Webb looks, as though the young universe moved through entire developmental stages before standard models believe enough time had passed for them to occur at all. Inside enormous data centers, cosmologists build universes from mathematics. They begin with tiny fluctuations measured in the cosmic microwave background, distribute dark matter through simulated space, apply gravity, gas dynamics, radiation, feedback, and cosmic expansion, then let billions of virtual years unfold inside supercomputers. These are cosmological simulations. Projects like Illustris, Eagle, Illustris TNG, and Simba represent some of the most sophisticated attempts ever made to reproduce the universe from first principles. They are not animations or artistic approximations. They are numerical laboratories designed to test whether known physics can evolve the early universe into the one we observe today. For years, they worked remarkably well. Large-scale structure emerged naturally, galaxies clustered realistically. Star formation histories broadly matched observations across much of cosmic time. Simulations became one of the strongest pieces of evidence supporting lambda CDM because independent teams using different methods repeatedly produced similar large-scale universes. And they all predicted the same thing at high redshift. The first galaxies should appear small, irregular, chaotic, and relatively low in mass. Hierarchical structure formation, the idea that small systems merge gradually into larger ones, requires time. Early galaxies should therefore resemble rough beginnings rather than mature structures. But Webb saw something else. Massive galaxies appeared too early by factors difficult to ignore. In certain mass ranges and epochs, observations exceed simulation predictions by factors of 10, 100, or even 1000 depending on the assumptions used. Structures expected to remain rare or non-existent became common enough to challenge the underlying models directly. Simulation teams responded quickly. New runs now incorporate modified assumptions, higher star formation efficiencies, altered feedback prescriptions, evolving dark energy behavior, and even primordial black hole seeds intended to accelerate collapse in the early universe. Researchers are effectively adjusting the initial conditions and physical recipes to see what combinations reproduce Webb's observations more successfully. Some models can produce earlier massive galaxies now, but often only under uncomfortable conditions. Parameters must sometimes be pushed toward values many cosmologists consider physically unrealistic, reducing feedback dramatically or converting unusually large fractions of gas directly into stars. In some cases, simulations only succeed after fine-tuning assumptions specifically to force agreement with Webb data. That itself becomes meaningful. Because simulations are not separate from theory, they are theory translated into mathematics. Every successful prediction reflects physical assumptions embedded into the model beforehand. When simulations fail consistently against observation, it usually means some physical ingredient is missing, incomplete, or incorrect. One especially important parameter is the stellar to halo mass ratio. This measures how much of a dark matter halo's total mass ultimately becomes stars. Standard simulations predict relatively modest ratios because feedback expels large amounts of gas before it forms stars efficiently. But Webb's early galaxies appear to contain far more stellar mass relative to their inferred halos than simulations expected. The galaxies converted matter into stars too effectively. That discrepancy cuts directly into the core assumptions governing galaxy evolution. Either halos formed differently, gas cooled differently, feedback behaved differently, or some entirely unknown process altered structure formation in the young universe. Simulations remain among the most powerful tools cosmology possesses because they force theories into quantitative predictions. They reveal whether our equations can actually build the universe we observe. Webb is now exposing the places where those equations stop matching reality, not symbolically, but numerically. When observations stop fitting comfortably inside an established model, cosmology does what science has always done. It tests alternatives. Some survive briefly, most fail. A few evolve into serious candidates for future refinement. The ideas surrounding Webb's discoveries exist inside that process now, neither accepted consensus nor simple fringe speculation. They occupy the uncertain middle ground. One older concept, returning cautiously into discussion, is the steady state universe, originally associated with astronomer Fred Hoyle during the 1940s. In its original form, the theory proposed that the universe has no beginning and maintains constant large-scale density through continuous matter creation as expansion occurs. The model lost favor decades ago. Observations of the cosmic microwave background and galaxy evolution strongly supported the Big Bang instead. Yet Webb's timing problems have prompted a small number of researchers to revisit eternal cosmologies in modified forms, asking whether certain assumptions about cosmic age and structure formation deserve reconsideration. Another proposal comes from Roger Penrose and his conformal cyclic cosmology, usually shortened to CCC. In this framework, the universe undergoes repeating cycles where one cosmic epoch transitions into another through extreme expansion. Each cycle effectively becomes the next Big Bang. According to the idea, traces may survive between cycles. Penrose and collaborators have argued that unusual patterns inside the cosmic microwave background could represent signatures inherited from a previous cosmic era. Those claims remain heavily contested, with other researchers unable to confirm the evidence convincingly. Then there is plasma cosmology. This approach emphasizes electromagnetic forces over gravity as the dominant architect of large-scale structure. Most mainstream cosmologists reject it because it struggles to reproduce observations that lambda CDM explains successfully. Still, Webb's discoveries occasionally revive public interest in alternative frameworks, emphasizing neglected physical processes. More serious attention remains focused on modified gravity. Rather than adding invisible dark matter, theories like MOND, TVES, and relativistic MOND variants alter gravity itself under specific conditions. Some formulations generate faster early structure growth than standard cosmology predicts, potentially easing tension with Webb's massive galaxies. But the trade-offs remain severe. Models improving galaxy formation sometimes fail against the cosmic microwave background or galaxy cluster observations. Solutions emerge in one region of cosmology while new contradictions appear elsewhere. Another possibility reaches even deeper into theoretical physics. Certain string theory inspired models propose additional spatial dimensions beyond the familiar three. If gravity leaks or behaves differently across those hidden dimensions, cosmic structure formation during the early universe might proceed more rapidly than current equations predict. The mathematics become highly speculative there. No higher dimensions have ever been observed directly, yet these frameworks remain active areas of theoretical research because they attempt to unify gravity with quantum physics while naturally modifying cosmological behavior at extreme scales. And that is the important distinction running through all these alternatives. None explains everything cleanly. Lambda CDM still succeeds remarkably well across enormous portions of cosmology. It predicts the cosmic microwave background accurately, reproduces large scale structure broadly, and explains expansion history across billions of years. The model is not collapsing completely under Webb's data, it is straining in specific places. That matters because scientific revolutions rarely replace successful frameworks wholesale. More often, they add missing ingredients, revise assumptions, or expand older theories into broader forms. The most likely resolution to Webb's discoveries may not be an entirely new cosmology, but a refinement inside the existing one. The difficulty is that no one yet knows what the missing ingredient actually is. Webb is still in the early phase of its scientific life. Most of the data reshaping cosmology so far has come from only a handful of observing campaigns, examining extraordinarily small regions of sky. Yet those narrow windows already contain more ancient galaxies than many astronomers expected to find across far larger volumes. The search is accelerating now. Programs like Cosmos Web, Primer, Uncover, and the continuing JADES releases are all focused heavily on high redshift structure formation. Each survey approaches the early universe differently. Some prioritize depth, staring at tiny regions for hundreds of hours. Others prioritize wider coverage, searching for statistical patterns across larger cosmic environments. Together, they are expanding the timeline outward. One major target involves galaxies beyond redshift 20. If such objects exist and Webb confirms them spectroscopically, they would push visible structure formation even closer to the beginning of cosmic history. Webb possesses the theoretical infrared sensitivity to detect candidates that distant, although confirmation becomes increasingly difficult as the signals weaken and cosmic expansion stretches the light further. Another priority concerns population. 3 stars. Astronomers are searching for specific spectral signatures indicating pristine stellar populations formed from nearly pure hydrogen and helium. Certain emission line ratios inside galaxy spectra could reveal chemical environments untouched by previous generations of stellar enrichment. Detecting those signals directly would provide the clearest evidence yet that Webb is observing systems approaching the universe's true first light. Gravity itself is helping with the search. Through gravitational lensing, massive foreground galaxy clusters bend and magnify light from far more distant background objects. The effect acts like a natural cosmic telescope. Webb uses these distorted regions to detect galaxies otherwise too faint to observe directly. Some of the earliest candidate structures identified so far appear only because intervening gravity amplified their light enough to reach Webb's detectors. Even older survey regions are being revisited. The Hubble Ultra Deep Field, perhaps the most studied patch of sky in astronomical history, now looks profoundly different through Webb's infrared instruments. Objects completely invisible to Hubble emerge clearly in the new data, including ancient galaxies hidden by cosmic expansion beyond Hubble's observational range. Researchers are also mapping reionization itself. By tracing how ionized and neutral regions were distributed across the early universe, Webb can reconstruct the spatial geometry of the Epoch of Reionization and connect it directly to galaxy overdensities already observed at extreme redshifts. The goal is not simply finding ancient galaxies anymore. It is reconstructing how the first luminous structures transformed surrounding space. And Webb has time. Fuel estimates now suggest the observatory could remain operational for more than 20 years, potentially collecting data well into the 2040s. Every future observing cycle increases the statistical power of the discoveries, already forcing cosmologists to reconsider structure formation timelines. Another instrument will eventually widen the search dramatically. NASA's upcoming Nancy Grace Roman Space Telescope is designed for enormous wide field surveys, covering areas thousands of times larger than Webb's narrow fields, while still reaching deep cosmic distances. Webb provides exquisite close examination. Roman will provide population scale context. That distinction matters because everything reshaping cosmology right now originates from remarkably tiny fractions of the sky. The anomalies may grow stronger with larger samples. They may weaken. Entirely new structures may emerge instead. At this stage, the observable universe Webb has revealed is still only a thin and incomplete slice of a much larger picture beginning to form. For most of human history, physics was built from local experience, falling objects, flowing water, fire, motion, light, but modern cosmology changed that relationship completely. Now the universe itself functions as a laboratory, one so large that its structure tests physical laws under conditions impossible to reproduce anywhere else. That is why these observations matter so deeply. When we study galaxies forming only a few 100 million years after the Big Bang, we are not simply cataloging distant objects. We are testing gravity, thermodynamics, quantum mechanics, and space-time itself under extreme conditions that existed near the beginning of cosmic history. The cosmological principle sits beneath much of this framework. It assumes that at sufficiently large scales, the universe is statistically uniform in every direction. That assumption allows Einstein's equations of general relativity to be applied cleanly across cosmic distances. Remove that uniformity, and many related calculations become unstable or incomplete. Predictions involving gravitational wave propagation, black hole entropy, and quantum field theory in curved spacetime all depend, indirectly, on the large-scale geometry of the universe behaving consistently. But Webb keeps pressuring that geometry. The fine-tuning problem becomes sharper as well. Cosmologists already understood that the early universe required extraordinarily precise initial conditions for stars, galaxies, chemistry, and eventually life to emerge. Tiny changes in density fluctuations after the Big Bang would have produced a radically different cosmos. Yet, if structure formed even earlier and faster than predicted, those initial conditions may have been even more delicately balanced than current models suggest. Another unresolved problem grows larger here. Quantum field theory predicts that empty space should contain an immense vacuum energy density generated by fluctuating quantum fields. But observed dark energy is incomprehensibly smaller. The mismatch reaches roughly 1 part in 10 to the power of 120, often described as the worst theoretical prediction in physics. If DESI data hinting at variable dark energy prove correct, that discrepancy becomes harder to reconcile rather than easier. Several quantum gravity frameworks attempt to approach these questions differently. String theory proposes additional spatial dimensions and vibrating fundamental strings beneath particle physics. Loop quantum gravity treats spacetime itself as quantized, composed of discrete geometric units. Causal set theory instead models spacetime as a growing network of ordered events. Each framework predicts different behavior during the universe's earliest moments, particularly near the Planck epoch, the unimaginably brief interval where gravity and quantum mechanics should merge. Webb may now be constraining those ideas observationally. Some physicists have begun considering whether the anomalies emerging at high redshift reflect quantum gravity effects influencing cosmological structure formation at unexpectedly large scales. Under ordinary circumstances, Planck scale physics should remain hidden far beyond direct observation. But the early universe operated under densities and temperatures so extreme that microscopic physics may have shaped cosmic evolution in ways still visible today. Even the anthropic principle shifts under this pressure. That principle argues we observe a life permitting universe because only such a universe allows observers to exist. But if cosmic structure varies significantly across enormous regions, then the conditions supporting galaxies, stars, and stable chemistry may themselves be highly localized rather than universal, which changes the role of Webb entirely. It is not merely observing ancient galaxies, it is probing the deepest layer of physical reality we can currently access, the hidden architecture governing how matter, spacetime, energy, and existence itself are organized across the universe. Enrico Fermi asked the question casually in 1950 during a lunch conversation about extraterrestrial life. If the universe contains billions of stars, billions of planets, and countless opportunities for biology to emerge, where is everyone? The paradox endured because the numbers seemed overwhelming. Even conservative estimates suggested that life should not be rare. The Milky Way alone contains roughly 100 billion stars. Modern surveys indicate that planets are common, perhaps more common than stars themselves. Once astronomy confirmed that chemistry spreads naturally through galaxies, the possibility of habitable worlds stopped feeling exceptional. But those assumptions depended on a particular cosmic timeline. The standard picture imagined a universe slowly becoming suitable for life over billions of years. First, stars formed, then heavier elements accumulated gradually through generations of stellar death. Rocky planets emerged later after enough carbon, oxygen, silicon, and iron existed to build them. Under that framework, life bearing worlds may have become widespread only several billion years after the Big Bang. Webb complicates that sequence. If chemically mature galaxies already existed at redshift 14, then the ingredients for planets may have appeared astonishingly early. Oxygen, carbon, and nitrogen were already circulating through some systems less than 300 million years after cosmic expansion began. That means rocky worlds, at least in principle, could have formed within the universe's first billion years, which changes the scale completely. A civilization emerging in one of those galaxies would not precede humanity by thousands or millions of years. It would precede us by roughly 12 billion years. Entire geological eras on Earth become negligible beside that difference. Human civilization itself occupies less than a flicker of cosmic time. But the paradox shifts here into something stranger. The question is no longer simply where intelligent life might exist today. Instead, we begin wondering what happened to whatever emerged first. If ancient, overdense regions formed stars, planets, and potentially biology at accelerated rates, then the oldest inhabited parts of the universe may already be unrecognizable. Their brightest stars would have died long ago. Galaxies may have collided repeatedly, reshaping themselves over billions of years. Black holes would have grown. Planetary systems would have destabilized. Some regions may now be silent ruins. This connects uneasily to the large-scale structures Webb and other surveys continue identifying. Overdense cosmic environments form earlier, evolve faster, and exhaust fuel sooner. If intelligence follows complexity, then the oldest potential civilizations may have appeared precisely inside those ancient concentrated regions, now visible only as distant red-shifted structures. And still, we detect nothing, no engineered signals, no unmistakable astroengineering, no clear evidence that life persists across cosmic distances. The silence itself becomes information. In a universe assembling structure faster than expected, civilizations may also rise and disappear faster than we imagined. That possibility carries a different emotional weight. Perhaps humanity is not standing near the beginning of cosmic history, looking forward into untouched time. Perhaps we exist after immense forgotten cycles of stellar evolution already unfolded elsewhere, long before Earth formed from the remnants of older stars. We may not be early observers in a young universe. We may be late arrivals in one whose first chapter ended billions of years ago and whose oldest stories survive only as faint light finally reaching us now. If you step outside on a clear night and look toward the pale band crossing the sky, you are looking sideways through the structure that made us. The Milky Way surrounds us completely, a rotating disk of stars, dust, gas, and dark matter stretching roughly 100,000 light years across. For most of modern astronomy, it felt immense. But Webb has quietly changed the scale of comparison. Our galaxy is old by human standards, yet not especially ancient cosmologically. The oldest stars in the Milky Way's halo formed around 13 billion years ago, shortly after the first stellar populations emerged anywhere in the universe. But the thin stellar disk, the organized rotating structure where our sun resides, began assembling much later, roughly 8 to 10 billion years ago, through gradual accretion, mergers, and sustained star formation, which places us somewhere in the middle. The Milky Way is not among the universe's first galaxies. It formed from material already transformed many times before. Earlier generations of stars had already lived and died elsewhere, enriching interstellar gas with carbon, oxygen, silicon, magnesium, and iron, long before the Sun condensed from a molecular cloud about 4.6 billion years ago. Everything around you carries that inheritance. The calcium in bone, the oxygen in blood, the silicon inside stone, all were forged inside stars that existed before our galaxy fully stabilized. Webb's observations sharpen that realization because they reveal that chemical enrichment began astonishingly early, inside structures already evolving rapidly near cosmic dawn. Our location inside the cosmic web also matters. The Milky Way belongs to the Local Group, a modest gravitational collection containing Andromeda, Triangulum, and roughly 50 smaller dwarf galaxies. Compared with the enormous overdense regions Webb observes at high redshift, this is a remarkably calm environment. We do not inhabit a crowded supercluster core filled with violent starbursts and constant galaxy collisions. We exist in a quieter filamentary region between larger concentrations of matter. There is nothing central about it. Not our galaxy, not our cluster, not our era. But that perspective becomes strangely grounding rather than diminishing. The universe no longer appears organized around a single privileged viewpoint. Instead, it resembles an evolving landscape of regions developing at different rates, under different conditions, across immense spans of time. Even our calm neighborhood is temporary. Andromeda, currently 2.5 million light years away, is moving toward the Milky Way at roughly 250,000 miles per hour. In about 4.5 billion years, the galaxies will begin merging. Spiral arms will distort, gas clouds will compress, new waves of star formation will ignite, while older stellar orbits scatter into unfamiliar shapes. Galaxies are not fixed islands. They drift, collide, grow, and dissolve continuously across cosmic history. Now imagine observing from one of the ancient overdensities Webb has uncovered, where neighboring galaxies crowded the sky and star formation erupted across enormous regions simultaneously. The night there may have looked radically different from ours, brighter, denser, more active, filled with structures evolving at accelerated speed. We emerged somewhere else entirely, in a quieter region, during a later era, inside a galaxy assembled from the ashes of much older systems. That is not a statement of insignificance. It is simply our cosmic address, one location inside a universe now revealed to be stranger, older, and more varied than we once believed. Somewhere beyond the reach of unaided vision, a galaxy released a stream of infrared light more than 13 billion years ago. That light crossed expanding space continuously, long before Earth existed, long before the Sun ignited, long before our galaxy completed its current shape. Eventually, in a narrow interval of modern time, a segmented mirror orbiting near the second Lagrange point intercepted a fraction of those photons. And now we study them. There is something deeply unusual about this process. Every Webb observation carries an unavoidable delay built into reality itself. Light travels at a finite speed, about 186,000 miles per second, fast enough to circle Earth several times in 1 second. Yet across cosmic distances, even light requires billions of years to arrive, which means distance becomes time. The galaxy JADES GSZ140, as we currently analyze it, existed roughly 290 million years after the Big Bang. But the actual object, whatever form it has today, lies unimaginably farther along its history. Across 13.5 billion additional years, stars would have formed and died repeatedly. Galaxies may have merged into it. Black holes may have consumed its central regions. Its original structure could be entirely unrecognizable now. We cannot know directly. That creates a strange observational condition unique to cosmology. We never observe the universe as it exists simultaneously. Instead, every direction in the sky contains different ages layered together. The moon appears about 1 second in the past, the sun 8 minutes, Andromeda 2.5 million years. Distant quasars arrive from epochs before Earth formed at all. The deepest Webb fields extend this layering dramatically. Those images are not simple photographs of space. They are stacked records of cosmic history, where each increasing distance corresponds to an earlier chapter in the universe's development. Nearby galaxies belong to relatively mature epochs. Fainter, redder objects emerge from progressively younger cosmic eras. At the deepest limits, we approach the first generations of structure itself. No other human sense operates this way. You hear sound after a delay, but only briefly. You smell chemicals after they drift through air. Yet no ordinary experience grants direct physical access to ancient time preserved intact across billions of years. Astronomy alone turns the past into an observable object. But this also means the universe we describe scientifically is partly reconstructed. When cosmologists speak about the universe being 13.8 billion years old, composed of dark matter, dark energy, ordinary matter, and evolving structure, they are assembling a coherent model from signals originating at vastly different distances and therefore vastly different moments. The map is extraordinarily precise, but it remains a model inferred from incomplete temporal fragments. Webb has sharpened awareness of that incompleteness, not by destroying the standard cosmological picture, but by exposing measurable gaps between prediction and observation. The universe described by Lambda CDM remains powerful, predictive, and deeply successful, yet it now appears less final than once imagined. More provisional, every photon Webb captures arrives from something altered by time beyond our ability to witness directly. In that sense, astronomy resembles excavation more than observation. Each spectrum functions like a buried artifact carried across cosmic distance, and Webb is the deepest archaeological instrument humanity has ever built. At the center of modern cosmology sits a growing collection of questions that no longer feel comfortably isolated from one another. They overlap now, tugging at the same assumptions from different directions across different scales of the universe. Why do some early galaxies appear so massive, so quickly? That problem alone remains unresolved. According to standard structure formation models, many of the systems Webb observes should not have accumulated enough stars, gas, or dark matter halos within the available time after the Big Bang. Yet, they exist as direct observational data, not theoretical possibilities. Then there are the strange geometries. The Big Ring and the giant arc extend across distances so enormous that they strain expectations of cosmic uniformity. Their shapes are difficult to explain through known mechanisms of gravitational clustering alone. Are they statistical accidents, hidden projection effects, or evidence that matter distribution becomes more structured at large scales than our models assume? That question connects directly to the cosmological principle itself. If structures exceeding 1 billion light years truly violate large scale uniformity, then parts of modern cosmology require revision at a foundational level, not abandonment. Revision. General relativity would still function locally. The cosmic microwave background would still exist, but the assumptions linking those observations into a coherent global model might need adjustment. The black holes deepen the uncertainty. Quasars above redshift 7 contain central black holes reaching hundreds of millions or billions of solar masses far too early in cosmic history. What seeded them? Direct collapse mechanisms remain hypothetical. Primordial black holes remain unconfirmed. Super Eddington accretion remains observationally uncertain. Dark energy introduces another layer. Is it truly constant across time, as the cosmological constant predicts, or evolving slowly, as DESI observations tentatively suggest? If cosmic expansion behaved differently in the past, then estimates of age, growth rate, and structure formation timelines all become more flexible than previously assumed. Even the age of the universe itself re enters discussion here. 13.8 billion years remains the best supported estimate available. But that value depends on cosmological assumptions now being stress tested by Webb data. If those assumptions shift, derived measurements may shift with them. The Hubble tension still persists as well. Measurements based on the early universe disagree with measurements derived from nearby galaxies by roughly 8 to 9%. Large-scale inhomogeneity may contribute, or perhaps entirely different physics is involved. And beyond all of this lies the question of the first stars. Did population 3 stars form quickly enough, burn rapidly enough, and chemically enrich surrounding gas efficiently enough to explain the oxygen, nitrogen, and carbon Webb detects at extreme redshift? Current evidence suggests possibly, but certainty remains distant. What matters is that none of these mysteries are beyond investigation. Each has planned observational tests already underway through Webb, the upcoming Nancy Grace Roman Space Telescope, and next generation observatories like the Extremely Large Telescope. Spectroscopy will improve, survey volumes will expand, simulations will evolve, and the scientific response has been remarkably disciplined. Not panic, not denial, more measurements, more models, more debate. Exactly the behavior science is designed to produce when reality refuses to fit comfortably inside existing expectations. There is something beautiful about witnessing that process directly. The old map was not useless. It brought us extraordinarily far, but Webb revealed coastlines beyond its edges, structures hidden in the dark, distances folded differently than expected. Not knowing is not failure. Not knowing, while continuing to build better instruments and ask sharper questions about the universe, is the entire project of science itself. For all the precision of modern astronomy, most of the universe remains physically invisible to us, not hidden behind dust clouds or distant beyond detection, but fundamentally unseen. Dark matter reveals itself only through gravity. Dark energy reveals itself only through cosmic expansion. Together, they account for roughly 95% of the universe's total content. Everything familiar belongs to the remaining fraction. Stars, planets, oceans, galaxies, human beings. Every atom your body contains exists inside the thin visible layer. Cosmology calls baryonic matter, ordinary matter composed of protons, neutrons, and electrons. The entire history of human observation emerged from that narrow category, and from it, we extrapolated outward. The standard cosmological model became extraordinarily successful by using visible structure, gravitational behavior, and background radiation to infer the properties of the unseen majority. Lambda CDM explained galaxy clustering, cosmic expansion, microwave background fluctuations, and large-scale structure with remarkable accuracy. But Webb is beginning to expose the limits of that extrapolation. The pattern is familiar historically. Each major revision in cosmology expanded the scale of our ignorance rather than reducing it. Copernicus displaced Earth from the center of the cosmos. Edwin Hubble demonstrated that the Milky Way was only one galaxy among billions. Then, in 1998, distant supernova measurements revealed that cosmic expansion was accelerating because of an unknown force later called dark energy. Every discovery widened the horizon. Now Webb appears to be continuing that sequence. The early universe no longer looks as simple or gradual as expected. Structure formed faster. Galaxies matured earlier. Chemical enrichment advanced rapidly. The map still functions, but the territory contains features previously absent from it. And even that territory is limited. There exists a boundary called the cosmic horizon, the maximum distance from which light has had time to reach us since the Big Bang. That boundary lies roughly 46 billion light years away in every direction because space itself expanded while light traveled through it. Beyond that horizon, observation ends. Not because nothing exists there, but because information from those regions has never reached Earth. The observable universe is therefore not the whole universe. It is only the portion causally connected to us since cosmic expansion began. What lies beyond remains genuinely uncertain. The universe may extend infinitely. Space may curve back onto itself across unimaginable distances. Physical constants may vary between regions. Entire structures, larger than anything Webb currently observes, may exist permanently outside observational reach. That possibility changes the emotional scale of these discoveries. The rings, arcs, filaments, voids, and ancient galaxies now challenging cosmology may represent only tiny local expressions of patterns repeated across distances we will never directly witness. If the universe is infinite, then every structure we observe likely has analogs elsewhere, altered slightly, recombined differently, stretched across other cosmic environments endlessly. We are not seeing the full story. We are seeing one accessible section of it, limited by the age of the cosmos and the speed of light itself. Webb has pushed human observation closer to that boundary than ever before. Yet the deeper it looks, the more obvious the boundary becomes. The universe is not obligated to conform neatly to the models we build from partial information. It never promised simplicity. Long before the first Webb image reached Earth, the telescope already carried decades of accumulated human time inside it. Engineers began designing its earliest concepts in the late 1990s. Entire careers unfolded during its construction. Graduate students became professors while waiting for launch approval. Children born when development started were adults by the time the observatory finally left Earth. More than 10,000 people contributed across 14 countries. The project absorbed nearly $10 billion, survived political threats, technical failures, schedule collapses, and repeated redesigns. At several points, cancellation seemed possible. The telescope became so ambitious that many doubted it could ever function as intended. Then came December 25th, 2021. An Ariane 5 rocket lifted Webb into the night sky from French Guiana, carrying one of the most complex scientific instruments ever built. But launch was only the beginning. Webb traveled toward the second Lagrange point, usually shortened to L2, a gravitational balance region, roughly 1.5 million kilometers from Earth, where the observatory could maintain thermal stability while orbiting the Sun alongside our planet. The journey lasted 6 months. During that period, Webb unfolded itself piece by piece in deep space. The sunshield deployed first, thinner than paper and spread across 5 delicate layers the size of a tennis court. Then the mirror segments rotated outward, antennas locked into place, instruments cooled gradually toward operating temperature. Every stage carried risk. NASA identified 344 single-point failures during deployment, moments where one malfunction could permanently end the mission. Engineers monitored telemetry in near silence as commands traveled across space and confirmations returned minutes later. All 344 succeeded. When the first calibration images appeared, scientists around the world reacted with something quieter than celebration. Relief, mostly. Many had spent their entire professional lives preparing for this telescope. Some researchers who helped design Webb's instruments never lived to see launch. Others watched the first images emerge from offices they had occupied for decades. Then the anomalies began appearing. Galaxies too bright, structures too large, black holes too massive. Instead of confirming expectations neatly, Webb opened new questions almost immediately. But within science, an impossible observation is not bad news, it is opportunity. Every contradiction means nature still contains undiscovered rules. Astronomy has always advanced this way. Galileo's refractor overturned the perfect heavens. The 200-inch Palomar telescope expanded the known scale of galaxies. Hubble revealed accelerating expansion. Webb now joins that lineage, another instrument pushing human understanding beyond its previous edge. And already, successors are being imagined. Future observatories may directly image Earth-sized planets around nearby stars, analyze atmospheric chemistry for biological signatures, and observe structure formation beyond Webb's current limits. New mirror designs, interferometers, and infrared systems are already under discussion. The questions never disappear. They become sharper, narrower, and more profound as instruments improve. No telescope delivers a final answer because the universe is not a puzzle with a finished edge. It is a landscape that expands as we enter it. We continue building telescopes for the same reason humans always crossed oceans, climbed mountains, and mapped unfamiliar skies. We cannot stop looking beyond the horizon. Tonight, the night sky above you looks unchanged. The same constellations still cross the horizon. The same pale band of the Milky Way still stretches overhead, where darkness is deep enough to reveal it. Stars appear fixed, silent, permanent. Human beings have looked upward at them for tens of thousands of years and seen familiarity there. But the sky is not showing you the present. Every point of light overhead is delayed information, moving toward you across space at 186,000 miles per second. Some of that light began traveling before cities existed, some before agriculture, some before human beings themselves, and some before Earth existed at all. The Andromeda Galaxy, faintly visible to the naked eye under clear conditions, sits roughly 2.5 million light-years away. The light reaching your eyes tonight departed when early human ancestors still shaped stone tools beside African rivers. Entire species appeared and vanished during its journey here. That alone reshapes the sky. But Webb extended this perspective almost to the beginning of cosmic history itself. Its infrared mirrors now observe galaxies whose light has traveled for 13.5 billion years, arriving from an era when the universe was still assembling its first large structures. And what Webb found there was not simplicity. The Big Ring stretches across 1.3 billion light-years, in apparent defiance of the large-scale uniformity our models predict. Massive galaxies appear at epochs where structure should still be small and chaotic. Black holes, with billions of solar masses, already exist, while the universe itself remains younger than many stellar growth models permit. And yet, they are there. That phrase matters. The universe is not negotiating with our equations. Physical reality does not pause when models become uncomfortable. Webb did not invent these structures. It revealed them. The light already existed, crossing space long before human beings developed mathematics capable of describing galaxies at all. We are encountering a universe that behaves according to its own history. And we are part of that history too. The calcium in your bones, the oxygen you breathe, the iron carried through your blood, all of it formed inside stars that lived and died before the sun existed. Earlier generations of stars fused simple hydrogen into heavier elements, then scattered those materials outward through supernova explosions. Later, stars inherited that chemistry. Then planets formed from the remnants. Then eventually, you. Across billions of years, matter learned increasing complexity. Clouds became stars. Stars produced chemistry. Chemistry assembled biology. Biology evolved awareness. And awareness built instruments capable of looking backward through time toward the first structures that made everything else possible. That continuity is easy to miss, but it places us inside the same unfolding process Webb is observing. We are not separate from cosmic history. We are one of its outcomes, examining the older chapters that produced us. And what those chapters reveal is a universe more active, more uneven, and more extravagant than we expected. Galaxies emerged faster, structures formed earlier, complexity arrived sooner. The cosmos was building intensely long before we understood the scale of what it was making. And we are only beginning to learn how to read the record it left behind.